and runs over to a quarter watt LED light bulb. We'll now charge the tank. Send air to the turbine.
Whoa! Look at that. What's the relevance of that relative to what we've been talking about? No? No takers? Well, last time we were talking about compressibilities of liquids and gases. We said that liquids are very incompressible, but gases, following the ideal gas law, were quite compressible. So I was reading the Guardian this weekend, and there was this little Twitter thing of a new startup company in Texas who were busy pumping water down existing oil wells with the idea of using a kind of version of compressed air energy storage. So the idea is that renewables like photovoltaics and wind are intermittent. You get electricity when the wind blows for wind turbines, but you need electricity all the time, and so you need to store it in some way. And so one way to store it is to compress air, pump it underground into either a reservoir or a big underground cavern, and then when you need it, you reverse the flow, drive it back through a turbine, and you use that to level out. So you don't have big peaks in the demand or your supply. You have a nice, easy transition between them. And so would you want to use air in that, or would you want to use water in that? Why? Yeah, why? Because it's sustained. You know that if you pumped up a bicycle tire with water, you get a lousy ride, I guess, from it. But also, when you take the cap off and put your pen down in it to release it, it would flow for about a millisecond, and then it would be gone. You know that when you do it with air, then it just keeps on flowing because it's compressible. It has this stored strain energy in it. And so that's maybe relevant to what we talked about last time. Okay. So today, any questions before we get rolling? Homework's alive. I guess I get all kinds of questions like, is this stuff online? Yes, right? I don't know how many times I've said that. The other thing is, I'm not sure I did say, but the idea of a single credit at Penn State is a 1 credit course means an hour in the classroom, a lecture, and then 3 hours on your own doing things. And so if you are having a hard time with the things that we're talking about, then do use the resources that are available. There are many resources online, not least of which are probably 3 or 4 or 5 years in some cases worth of videos, some of which will be different in some aspects. And so I encourage you to use that. I did say the book's not required, but it is not required. You don't need it. But whether you need it intellectually for yourself to be able to fathom your way through what we're talking about is your decision yourself. And so $80 for a book in terms of the cost that you pay per credit hour, I think is something that you, if you're avoiding it because of the cost, there are other ways to do it, of course. There's a version of it in the library, but and you could probably photocopy your friend's one for that matter, or scan it, I guess, in this age. So think about your own education in a rational way. All right, today we're going to take a little break from what we've done in terms of jumping around, and I'll do most of the work that we're going to do today using handwriting. So you can choose how you wish to take notes or not. Before we get going, we're going to be talking about fluid statics. So we've talked about properties of fluids which we need. Density, viscosity, interfacial tension are 3 of the properties we've looked at. I'm going to turn the music off on this. What we'll talk about today is fluid pressures at a point, or fluid statics. So fluids that aren't moving. So these fluids could be in a swimming pool. It could be in the atmosphere around us. This I just think is interesting because it kind of epitomizes some of the things. When you look at your watch, if you use a watch today, you can probably mark people's ages by whether or not they don't or don't wear watches. When it says safe to 200 meters, It means that the fittings can withstand not leaking down to that kind of depth. Hold your breath for as long as you can. I took the first class I ever took at Penn State, I took last semester, which was a diving class. And one of the things you have to do is you have to swim the length of the pool underwater with your breath held. And so it's interesting. So when you start doing that, I could get maybe 10 yards of a 25-yard pool. And so you look on YouTube how to do it, and then you sit next to your computer holding your breath, practicing for a while. And it's actually amazing. You can really change the length of time that you can hold your breath. So you can do it for a minute quite easily. These people do it for maybe 3 or 4 minutes and can go down 150 meters. The reason for doing this originally would have been pearl diving in the Pacific or wherever, but really quite amazing in terms of a feat of being able to do this. And of course, as you go down, you know that the pressure will change around you. And so what we'd like to do is be able to say something about why that is the case. Let's try something else and see. The other thing, which isn't so obvious, but it's exactly the same principle, is that if you happen to want to climb Everest, then I think these are the Hillary steps, which is the last large hole before you get up to the summit, is that people wear oxygen. They wear oxygen not because there's less oxygen in the atmosphere, although there might be actually because of the partial pressures, but there's less atmosphere, period. And it acts in exactly the same way. The same reason that it gets high pressure when you dive to the bottom of a swimming pool is because you have this weight of fluid above you. The reason we feel 10 to the 5 pascals here is because we have the weight of the atmosphere above us. The nitrogen and some oxygen that goes up to us and finally dwindles as you go into the stratosphere and beyond, into space, right? And so it's just the weight of that being pulled down by gravity. So it's exactly the same principles that apply. And so we'll look at those principles today. All right. So that's the motivation, should you ever want to climb Everest. So I'll close that. What's the hum?
White noise.
Just white noise. Yeah, okay. I was more worried whether it's my computer, or the background audio on the computer. All right. So that's where we're starting off today. So we're going to do something slightly different. I don't like that noise. All right. So the deal today is, where are we? And really the question that we're looking at is fluid pressure at a point. At a point. So that's our idea. So what we could do is we could do this. If you take the canteen that some of you carry around with you, which has a fluid in it, and it has a cross-sectional area, it has some height to it, which we'll call Z, it has some fluid in it, which we'll give it some density. We're on this planet, and so we'll have an acceleration due to gravity as well. And so what we could do is we could use this idea as a swimming pool, where this can is the fluid above us, which we're feeling in our ears. And what we could do is we could calculate exactly what the weight of this is going to be. And so we know that the weight is going to be equal to the mass of the fluid and the weightless container. So we'll make the container weightless because we can. It's going to be equal to the mass times gravity by definition. The mass is going to be equal to the volume times the density times gravity. And the volume is going to be equal to the area times the height. This is going to be our V, rho G. So that's what the weight of this container is. If we're sitting underneath it here, we know that from Newton, we have to push against it by a force which is equal to the weight. If it's one is equal to the other, it'll be in equilibrium, and therefore by definition it's not accelerating, and this is the force that we have to apply to do that. We know this force that we apply is going to be equal to or if we take this force and divide it by an area, that will be equal to a pressure. We'll call this pressure P, lowercase p as opposed to uppercase P, which is a force. And we know that these two, by definition, the pressure and the weight, have to be equal to each other. And so what we could do is we could merely substitute this into here, in which case we would write this as the pressure is equal to the force divided by the area, which, if I want to be pedantic, is equal to the weight divided by the area, which is equal to just this. Area, height of the can, density of the fluid, gravity divided by the area. Don't need those. And you've probably seen this, where the final expression, not surprisingly, is that the pressure is equal to the height of the can multiplied by density and gravity. Or if we write this as unit weight, just by definition, specific weight, unit weight, it's equal to density times unit weight. So you've probably seen that in your past. This chair keeps on going down on me. And so that may seem like a trivial thing to do, but what we could do is that now we could take this, and if I just scoot this up a little bit, let's kind of draw this off to the side just as we've done. So now we have this same container. Let's make a curve, a graph, an inverted graph. That noise is really annoying. And let's draw this down at some depth z, and we'll look at the pressure. So what we've done is, if we substitute in, for instance, the pressure at this point, the pressure at this point is going to be P1 is equal to the depth Z1 multiplied by the unit weight. And so this magnitude here, we're going to call P1. This is Z1. And by definition, we have a point. So we could also take two containers now, right? Stack two containers on top of each other, exactly the same size, both Z in height. And if we did that, then we'd go down to this second depth here. So we're supporting it on the base, we're holding it, we're cutting it off, we're holding everything above us, these two cans. Then we know that at at Z2, then we know that P2 is going to be equal to, well, the total depth of this is Z2, is just the same as a single container. You could imagine just adding them to each other. And so it's going to be equal to Z2 times unit weight. And that's going to give us another point here, which will be this. And this is P2. And I'm not very good at drawing lines, but you could imagine that if you made this container so short that Z was 0, then it must go through the origin. And so that's basically our description of how we could define what the fluid pressure does as you go down in the fluid. From a free surface at this point, where this is the top of the fluid, the container is weightless, and therefore we can calculate exactly what the behavior is. And so from this, if we wanted to generalize it, we could write this as the pressure is equal to depth multiplied by unit weight. We could take derivatives of both sides with respect to z. And if we do that, then merely we get out of it is that change in pressure is equal to change in elevation. Change in pressure with elevation is equal to the unit weight of the fluid. So that expression is absolutely general as it's written. It applies to liquids and gases alike locally, even though that fundamentally those materials are different. Liquids, we said, are incompressible, and so their density changes very little with the application of fluid pressure because they don't change in volume, in a controlled volume, but gases do. The other thing that we'd like to do is that we said before when we started this class, I know we talked about a lot of things, we said we'd talk about a coordinate system where we always took z as positively upwards. So we've drawn it as positively downwards down here. So you'll remember if you're in physics, I'm not being rude, the right-hand rule. The right-hand rule is that you turn your hand with this little triad upside down. X-coordinate is your thumb. Y-coordinate is your first finger. Z-coordinate is your middle finger. They're orthogonal to each other. And so we're going to choose Z upwards. And so if that's the case, then we're going to make this negative Z. If that's the case, then all that would mean is that this term here would be a negative. That's how I write negative. N-E-G-E-T-I is a minus. P-E is negative. And so this would just be a minus sign attached on this. It's just a sign convention. And so what it means is that we can look at the gradient of this line, because we're going to use calculus in this class. And if you think about this line here, we're going to write that change in pressure with elevation is equal to minus unit weight over 1. And so since this is a change in pressure here, this is a change in elevation here, or a negative one, then if we align these up so that pressure and unit weight align, then this would be, we could also draw this as a similar triangle, which happened to look like dz as being 1, and unit weight as being this. It's actually negative 1, I guess, right? But the same idea. And so the slope of this graph is some idea of what the unit weight is. We know that the unit weight of air is how many times less than that of water? 1,000. 1,000 kilograms cubic meter for water, 1 kilogram a cubic meter for air. And so that means if you did this, I should be very fancy with this. Oh, this is fantastic. If you did this curve for air, it might look like this as you go down because of this idea of this little triangle thing here. And if you did it for water, it would be really flat. But the same might hold. The caveat with that is that we made the case that this really applies for, well, we'll look at it next to see how it applies for other fluids. And so, strictly speaking, what we have here is the behavior for water, which is incompressible, because as you see, the unit weight of this is not changing as we go down in depth. The unit weight of this would change as we go down in depth, as if you had a gas, and we could calculate that merely by doing the kind of Everest example, right? We can perhaps show that to ourselves as you went up to Everest. So in other words, if we use this exact same analog for Everest, start off at sea level and go up to, what's the height of Everest? 30,000, yeah. So how many is that in SI? So we could do the same analog with a can of air, and we know that pressure is going to be equal to unit weight times Z, which is going to be 1 kilogram per meter cubed times 10 meters per second squared. This is rho G, right? Times 10 to the 4. If we multiply that out, we get 10 to the 5, 10 to the 5 kilogram meters per second squared, 1 over meter squared. This, by definition, 1 kilogram meter per second squared is what? Newton. I realized I didn't play with my units last time. May led to some of the confusion. So in other words, if you have a can of air, a weightless can of air, which is 10,000 meters tall, the pressure at the bottom of that column is going to be 10 to the 5 Pascal. Exactly what we feel here, just by happenstance. Which of course means that above the top of Everest, there's no air at all. The reality is that although the density of air at the bottom of this is about 1 kilogram per cubic meter, it's actually much, much less of this, as you'd expect. That's why you're breathing oxygen, and it changes gradually. And so the idea that the unit weight of the fluid is constant with depth is true for water, liquid, is probably not true for air. This is always true locally, depending on what the ambient pressure is, but it doesn't mean that this is then constant. Okay? So, all right. Everyone with us? So the other thing that we can do is we can also look at fluids which are static but accelerating. And so you're all very happy, I think, with what we did with these cans. But let's go back to our coordinate system and let's cast this in a slightly different way. This is our right-hand coordinate system. Positive Z is upwards. And instead of a canteen or a Nalgene bottle, to use a trade name, of water, our bucket of water is now cube. It has some dimensions to it, which are these differential dimensions. dy in the direction of the y coordinate, always positive. And what we're going to do is we're going to work on the same idea. We're going to have a fluid pressure which acts on the bottom. We're going to have a fluid pressure which acts on the top, but is changed from the magnitude on the bottom by some small amount, dp. And it's changed by some small amount because we've gone up in height by some amount. And of course, we don't know how it'll change, but it's going to be different from the amount before because we're holding this stuff up here. And if we ascended in the column, we know that it would become less pressure. So we're going to define this change as dp as we can. And we're also just going to multiply this by 1, right? dz over dz is just 1. So we haven't done anything to it particularly. We're going to define the top area of this as A. So that'll be this kind of area here. I guess it will have a fluid density which we'll call rho, and it will be acted on by gravity downwards. And I suppose it would have some weight to it, just as our other bottle did, of uppercase W. Okay? So what we're going to do now is we're going to make a slightly more general relationship. And we're going to come back and we're going to be excited, let me just do that, about our friend Isaac Newton. And we all know this. Newton's second law says that if you have forces acting on something, they have to be in balance with the accelerations that you're giving to that body. If the forces are exactly in balance, then the accelerations have to be zero and it's not moving. Not velocities, but accelerations have to be zero. We can think of this as a scalar quantity with only one component, a force in the x direction, accelerations in the x direction. Or we can also think about it as forces in the x and the y and the z directions being equal to masses times accelerations in the x and y and z directions, which we can also write, if you wanted to, as this. So the point is, what we did before, if I just scoot up quickly, is we did this only in the vertical direction. What we're going to do now is we're going to think about this in all directions. Okay? So what we could do is we can start now making this summation. Let's choose for the most interesting one is the z direction. And let's look at both the forces that are acting and the accelerations that can be applied to this. So the accelerations will be the same as me taking this cup of water, which is this cube, and moving it across in front of you from 0 to some velocity, and that is by definition acceleration. Still a fluid static because this fluid isn't circulating, but clearly the fluid is moving. It'd be like taking a drink in a car with you. Never do. So let's do some forces. So we have a force acting upwards. Acting upwards, we have P acting upwards. It acts on an area which is equal to A. It's positive because it's in the positive direction. And it's reacted against by this force acting downwards. So the force acting downwards is equal to, again, an area on which we have this force P plus dP dz times dz. So remember what we did here. We just an increment of pressure and a change in 1 times 1. We have a weight acting downwards, and that's going to be minus because it's acting downwards. The weight is going to be the volume, which is going to be equal to the area times dz. So this by definition is the volume. And it's going to be acted upon by acting upon the unit weight, gamma. And so these first terms, bless you, are F and MA is going to be the mass, which again is going to be equal to the area times dz times density times the acceleration in the z direction. So we're doing this equation here, basically. This part. We can clean that up a little bit, I think. What we could do, I suppose, is we could get rid of all of the areas. We could actually, let's not do that. Put those back in. What am I going to want to do? Yeah, all right. So we have this term here, plus, minus, a minus. So the only term that we're left with here is going to be dP dz times z, right? Because this and this cancel out, multiplied by area. We have an area times dz times unit weight here, and we have an area times dz times density times AZ. And so if we go back to gather terms, we know that area times dz is equal to the volume, right? The area is on the top here. dz is the height. So by definition, the product of those is the volume. And so in other words, this is a volume. The two terms at both ends of this are volumes. These two terms are volumes, and these two terms are volumes. So we could just divide by, multiply by 1 over volume. And if we do that, we end up with dp dz minus unit weight is equal to rho AZ. And I'm pretty sure I've left out a negative sign. This should be negative, right? So this is a minus, and this is a minus. And so sometimes we write this expression, I'm just going to rearrange it. We write this expression as, I'm going to write it as a partial derivative. So I'm going to write it as dp dz minus unit weight minus rho times AZ equals 0. So this is the component in the z direction. Okay, so instead of using canteens stacked on top of each other, we've used a canteen which is square, cubic, I guess. We figured out this one relationship here. We could do exactly the same by using pressures on all other faces to be able to figure out a similar relationship. The only thing on those other faces that we don't have acting on us is that clearly on those other faces we don't have weight acting. And so this term here that is unit weight, we wouldn't have. Yeah, go ahead.
Does it that equal minus d dz minus
Which one? This expression here?
2 up?
This.
Yeah.
So all I'm doing is I'm taking the terms that are the product of area times height, which is the volume, and then I'm going to divide this through by, by this term. So I'm dividing through by 1 over area times dz, which is the same as 1 over volume. That's what I've done. Yeah. So I think it's right. I'm pretty sure. I'm certain this is right. Not many things I'm certain about, but this one I am. So if we did it for the other directions, let's do it in reverse order. So you can imagine that if we did it in the y direction, we'd end up with minus change in pressure with y direction minus 0 minus density times acceleration in the y direction, which is just saying we're taking this canteen and we're accelerating it horizontally in the y direction. And in the x direction, we end up doing the same. And we end up with this. Again, there's no weight in the x direction, but this is the expression for acceleration in x. So these are expressions that we'll use today, but for the next actually 2 weeks. They're fundamental for what we'll do in the next couple of weeks. If you want to perhaps dissect these, so the reason we talked about the canteens first is that some people have surprisingly this aversion to calculus. But calculus is just summing things up in very small canteens that go in some place. And we've got exactly the same expression that we had before in this way. So for this week, we won't do anything with accelerations. So if we assume that acceleration is 0, so acceleration in the x direction is equal to y is equal to z is equal to 0. Not that gravity doesn't apply to us still, but the acceleration, so in other words, the stuff is sitting or moving at a velocity. It could be moving in an elevator at a constant velocity. The acceleration would be 0 if it's not accelerating. If that's the case, then we can take these expressions, and what do we end up with? If acceleration is equal to 0, then we lose these terms. And we would have something which is, if we rearrange it, we have minus dp dz minus gamma is equal to 0, unit weight, which is the same as saying change in pressure with elevation is equal to minus the unit weight. I think we've seen that somewhere today, right? But more importantly, in these other ones, we have that the change in pressure in the y direction is equal to 0. Could be minus, doesn't matter. Not doing a very good job here. X, right? Is equal to 0. And so those are two other important things. You can make this plus, makes it a bit easier maybe if it's plus, doesn't matter, right? So these things say two very important things. They say, first of all, that as we move up and down the fluid, the pressure change is always governed by the unit weight, the amount of stuff above us. We've kind of already said that. But these also say something very important as well. They say something that if we have a fluid with a free surface, and we are at some depth below that, we know that the pressure would build up at some rate according to z. It means if we go over a little bit further in this fluid, if this is the x direction, say here, and we look at the pressure at the same depth, then the pressures at these 2 points have to be the same. And so all this says, if we write this out a little differently, it says that the pressure change as you go in the x direction and as you go in the y direction is 0. So in other words, if you swim from here across here, the pressure you feel as you go from one to the other has to be the same. You have exactly the same amount of fluid above you, and therefore you shouldn't feel any change in pressure. So these expressions that we've derived here are the fundamental ones that we'll use. The main components that come out of it are, for the vertical one, that pressure changes with unit weight of the fluid. Absolutely true everywhere, but it doesn't mean that the unit weight is the same as everywhere, as it won't be in a gas. And that these two expressions for us now just say that you go horizontally in a fluid. If you go from here to Belfont and we're at the same elevation, the pressure in both places should be the same. Hence you can define your elevation by the pressure you measure in an iPhone or something. All right? Everyone okay with that? So, we didn't pay much heed to this, but this is really what we wanted to do today. We're partly there. We've got this expression, and we've also got these other two expressions. We know what coordinate system we'll always use. We've done it for what we've called an incompressible fluid, where gamma is constant. What about the expression where gamma is not constant? And this would be liquid, and this would be a gas. So those are the two other cases that we'd like to look at. So let's go back and do that. Okay? The easiest one is for a liquid. If we want to know how the pressure changes with elevation, z. Of course, this is z, but this would be 0, and this would be minus 10 meters, say. We know that the change in pressure with elevation is equal to minus unit weight. We also know that the change in pressure is equal to minus unit weight times dz. We know that we can integrate each of these from, this would be z1 and z2, in which case we'd have pressures P1 and P2. P1, P2, Z1, Z2. You know how to do this, right? This is just equal to the pressure evaluated between these limits of P1 and P2 is equal to minus unit weight times Z, Z1 and Z2. And in other words, it would be something like P2 minus P1, if you substitute the limits, is equal to minus the unit weight, Z2 minus Z1. Or if you wanted to, the pressure at 2 is equal to the pressure at 1 minus the unit weight times the difference in those elevations, Z2 minus Z1. You notice there's a minus sign here, but of course this Z2 is bigger than Z1. And so the term in the brackets is going to be negative. And so a negative and a negative comes out to be a positive. And so sometimes you might want to think of this just as delta Z, or Z, change in Z, in which case the pressure at this other place is going to be the pressure at one location plus unit weight times delta Z. And just from your own intuition, you'd know that as you go down in the fluid pressure will increase. So if delta Z is positive, unit weight is positive, this is on the surface, then you could surmise that the pressure down below you is going to increase by some amount. All right? So that's the first part. And that's predicated on the fact that gamma equals constant. It has to be constant, right? Because we've taken it within this integration sign, and we've taken it outside. And so we can't do that if it depends on Z. If pressure was changing with elevation, we'd have to leave it in. Okay? So this is 0. This is minus 10. And this is minus, so that's plus 10, which is this. So it works out. Okay? So if we believe that, you can always come back to that. Let's do it for a gas. Let's try and use the same kind of format. We'd like to be able to figure out how the pressure changes with depth. Take it on trust that instead of looking like this, it is going to look like this. So this is Z1, Z2. This is going to be P1. This is going to be P2. This is pressure. This is elevation. Remember what we said about what this means. We know that change in pressure with depth is equal to minus unit weight over 1. And by similar triangles, then this is dP, this is dz. And so if I draw another similar triangle here, it's a bit sketchy, dz would be 1, and this is unit weight. And so the fact that this is curving means that the unit weight is not constant. And so what we could do is we could do this again. We could write this out as a derivative. Change in pressure is equal to minus unit weight times dz, which is the same as minus density times gravity times dz. We know from the ideal gas law, which allows this to be the case, that pressure is equal to density times RT. Or alternatively, we could write this as density is equal to pressure over RT. All of a sudden I've changed my style. And so in other words, this can go in there. So we can write this as change in pressure is equal to gravity times pressure over RT. See, this term here, I'm just combining them, times dz. Do what we did before. Integrate both sides between P1 and P2 at elevation Z1 and Z2. We have to rearrange it a little bit first, right? Because we've got a pressure here that we should move onto the other side. So we're going to rearrange this as change in pressure. We're going to take this P onto the other side, divide it. We're going to do the integration, and we're going to do the integration on what's left, which is gravity, which is constant. We're going to assume the temperature is constant, and this. And if we integrate this, you know the integration is log P evaluated between these limits. I didn't move these limits down here, but the limits are P2 and P1 is equal to this integral again. It's just a constant, so it's G over, so long as temperature is constant, which it sometimes isn't in the atmosphere, multiplied by Z evaluated between these limits, Z2, Z1. And if you write that out in longhand, we end up with log P2 over P1 is equal to G over RT times elevation 2 minus elevation 1, in that order. It's not so easy to deal with that, so we can exponentiate it. We can multiply both sides by e to the x. If we do e to the x, then we end up with P2 over P1 is equal to exponential G over RT Z2 minus Z1. Did I lose a minus sign here? I think I did, right? There's a minus sign here, there's a minus sign here, there's a minus sign here, and there's a minus sign here. This is G, by the way, and this is to the power. And so in other words, if you want to know what the pressure is at point 2, it's equal to P1, pressure P1 multiplied by, just write this a different way so it's perhaps clearer, the exponential of minus G times the difference in elevation over ideal gas constant and temperature. And I won't plot it here. Let me just check whether that's right. Yeah, that's right. It's good to do something with once. Here's my cheat sheet. And so if we drew that, which is useful to do, we would find out that it actually physically looks, Well, actually, let's do this. Let's draw the surface of the ocean here at elevation z. Let's draw positive z in the vertical direction. This would be 10 to the 5 pascals. So this is 0 gauge pressure, 10 to the 5 pascal, 100 kPa absolute pressure. This is elevation. This is the water. This is a ship on the water. Toot toot. No humor. If we drew the trace for the air pressure, then it's limited by this magnitude here. And it starts very close to this axis and would come down through this point. This is an exponential curve, a very shaky exponential curve. And then once you hit water, it would go down as this. This would be dP dz is equal to minus unit weight over 1. This would be unit weight of water and 1 meter in height. At each of these locations here, this would be 1 meter height, and this would be the unit weight of air at that particular location. And so the important thing to see here is that certainly at the interface of the ocean is carrying all the weight of the atmosphere above it. So it has to be, at that point, the same pressure as the air pressure, just by equilibrium. Otherwise, the water would be accelerating, or the air would be accelerating into the other. And as you go below in the water, this expression is true everywhere. And because this is constant, this is just a straight line. This is also true as you go up in elevation here, but because the unit weight of air, the density of air is not constant, it's highest at the bottom, and it goes to a very small number, it goes to 0 as you get into space, then it changes. Amazing, right? Amazing. That's it. Any questions?